Okay, so there is a small sample. Of course, I could use a large sample, but I want to demonstrate using a small sample, the math behind it. So we've generated this sample. I'll show you the true value in R once we are done with this calculation. And we want to find the maximum likelihood estimator. Is the possible parameter values are theta1, theta2, theta3. And in this case, theta is nothing but p, right? We just call it theta. If you have multiple parameters, theta would be a vector, and you'll have a whole bunch of values. Now, what is the MLE for a binomial p-value? I mean, not a p-value, proportion.
Remind us of an MLE again.
Maximum likelihood estimator. Theoretically speaking, we know
Is it
We
x,
have-
x over n?
x over n, right? So, three, we want to measure the number of successes and want to find the probability of, the proportion or probability of success, which is,
So you got to 19.
I see, thank you. Like n times p hat would be equal to basic mistake 19, and it'll be 36 trials in total. So 19 over 36, what do we get?
It's just gonna be, so what, a little more than a half. It's
Huh?
gonna be a sixth more than a half.
We know it's more than half.
Just bigger.
But you guys don't have a calculator? I can do it, doesn't matter.
I don't know the last time I've used the calculator.
I mean, I know it's more than half too. Well, there we go.
It's just because if you did something with 6 trials 6 times, you attempted whatever you're doing 36 times total.
Right, so out of the 6 trials, you got 3. Right, so in total, you'd have 36.
Imagine they were all fractions. That was 3 out of 6, 4 out of 6, 3 out of 6, 4 out
Right.
of 5, and then you just added them all up. Actually, that doesn't make sense, but
Okay. The 3 out of 6, 4 out of 6, and you
Yeah.
take the average of those, well, you should get the same answer.
yeah.
Let's see. So we get 0.527a. Now, I'm giving you a set of theta values, in other words, p hat values. If these are given to you, then we can find a better estimate. In practice, though, that's not how things work. So the likelihood function, theta, given the data, how many data points do we have? 6. Yes? What is the likelihood function?
It's the product, the probability of that. I know it's the product.
Yes. Probability or the density of xi given each value of theta. Now, last time I mentioned that likelihood function, even though we can do it directly, the common approach would be to take logarithm on both sides and use log likelihood. I'll be effective, and instead of doing this, I'll just call it as d, indicating that's the data. And since I know the density of a binomial or probability mass function of a binomial,
N just be 6.
huh?
Should N just be 6?
Yeah. how do we find, well, what is the PMF of binomial?
It's p to the x, q to the n minus x times the combination x choose n. That's a combination x choose n, or n choose n, yeah, n choose n.
Good. You can split it up and write it as ln of n choose x plus xi ln of p plus n minus xi ln of 1 minus p.
Should we change the x to sixes? X is an n over there.
Now p once again is simply theta, so I can write it as theta. And not only that, this is a positive quantity. In other words, we are trying to find the maximum likelihood estimator based on the data and the parameter value. So would that matter to us? You're just adding a value, right? So in other words, ln of 6 choose xi, would it matter for each value of xi that I plug in? And different values of theta.
Not for different values.
Right, because we're going to change these two, right? That part will never change. So I could simply say this is proportional to, or how about approximately? Xi ln of p plus 6 minus xi ln of 1 minus p. And p in this case is nothing but the parameter theta. One and the same. Now, we've got multiple theta values. So theta 1 is equal to 0.81. So how do we go about doing this? Well, we'll start plugging values in. So 3 multiplied by ln of 0.81 plus 3 multiplied by ln of 1 minus 0.81, 0.19. 4 multiplied by ln of 0.81. Paul, are you with me?
Mhm.
Plus 2 ln of 0.19. Because I'm plugging in each xi. So x1, x2, x3, 3 ln of 0.81 plus 3 ln of 0.19 plus 4 ln of 0.81 plus 2 ln of 0.9 plus 5 ln of 0.81 plus 1 ln of 0.9. And the last term, of course, is 0.
What about the second half?
The first part right here is 0. I forgot that one. So plus 6 minus 0 is 6 ln of 0.19. So in total, we've got 6, 7, 9, 12, 14, 17 of ln of 0.19. And over here we'll have 5, 9, 12, 16, 19 of ln of 0.81. Yes, this is, if you put in the other theta values, would the 19 and the 17 change? No. So
Just
in general, I could write that log likelihood for this case, given the data, is 19 ln of theta plus 17 ln of 1 minus theta. Yes? Because no matter what P I have, I'm just looking at the same xi values. So at the end of the day, the only thing that's going to change would be 0.81 and 0.19. Yes.
Could you extend this somehow to any binomial distribution?
Yeah.
Because that's just what, the sum of x? That's just the sum of that minus x.
Yeah. We can come up with a general expression.
But it would it basically just be that?
Yeah. So, you know, you do sum of x, sum of n minus x, take the derivative, you find the maximum likelihood estimator, right? That's just how we do it. But in this case, since I have individual values, I'm just going to plug them in. So first case, theta 1 equals 0.81. (19 ln of 0.81 plus 17 ln of 0.19. What do we get? Negative value, right? The next case, theta 2, which I erased merrily. What is theta 2?
0.7.
0.7 exactly.
And the third is 0.7.
So 0.7 given the data. So 19 ln of 0.7 plus 17 ln of 0.3. And what do we get?
Negative 27.24.
Negative 27.24. And lastly,
0.74.
so 19 ln of 0.74 plus 17 ln of 0.3. Then bad math, 2/6. And what do we get?
Negative 28.62.
Negative 28.62. Good. So out of the 3 parameter values, which one maximizes the likelihood?
So
0.7.